Thank you. So, in our next session for today's talk, our next speaker is Professor Kenichi Morita. So, let me introduce him first, though he does not need any introduction, but still, just let me briefly tell about him that Professor Kenichi Morita is a Professor Emeritus of Hiroshima University. He received his Bachelor of Engineering, Masters of Engineering, and doctorate degrees from Osaka University in 1971, 1973, and 1978, respectively. From 1974 to 1987, he was a research associate of the Faculty of Engineering Science, Osaka University. From 1987 to 1990, he was an associate professor, and from 1990 to 1993, professor of Faculty of Engineering, Yamagata University. From 1993 to 2013, he was a professor of the Graduate School of Engineering, Hiroshima University. He has been engaged in the research of automata theory, reversible computing, and formal language theory. Related to unconventional computing, he studied many kinds of reversible computing models. They are universal reversible Turing machine, reversible counter machines, reversible cellular automata, reversible logic circuits composed of two-state reversible logic elements, and some others. Today, his talk is on time reversal symmetries in reversible cellular automata and their applications. So we welcome Professor Kenichi Morita to our webinar session. Welcome, sir. Over to you. Sir, you are not audible actually. Sir, we can't hear you. No, sir, we can't hear you.
Can you hear me?
Yes, we can hear you.
Okay. Thank you for your introduction. First of all, I would express my great thanks to the organizers of this meeting. Now, today I talk about time reversal. Sorry, I will show my slide. Can you see my slide?
Yes, sir, it is.
Okay. My talk is on time reversal symmetries in reversible cellular automata. At first, I give an outline of my today's talk. Reversible cellular automaton is called time reversal symmetric, T-symmetric for short. If its backward evolution is governed by the same local transition function for the forward evolution. The notion of T-symmetry comes from physics. I will show a simple example from physics. But here, T-symmetry is studied using elementary square partitioned cellular automaton, ESPCA, and elementary triangular partitioned CA, ETPCA. And obtained results are very useful for designing.
Morita, I'm sorry to interrupt you.
Yeah.
Sir, are you on the first slide?
Yeah, can you see my slide page 2? No?
No, no.
No. Why?
Sir, please share the whole screen.
Whole screen, it's maybe better. Okay. Whole screen. Okay.
There is option for industry.
Yeah.
Okay.
Yeah. Now it's visible.
Can you see?
Yeah,
Okay.
yeah, yes.
Okay.
Thank you.
Okay. Obtained results are useful for designing inverse functional modules in these reversible PCAs. First of all, I consider a very simple example of classical mechanics. By reversing momentum vectors of all particles, the system retraces its evolving process. For example, look at top left corner. There are many particles are moving, but at first it is at the bottom left corner. And randomly, momentum vectors are given to these particles, then evolve for some time. Then particle spreads in the box. At some time, reverse the momentum vectors of these particles simultaneously, and then evolve. Then the particle will go back to the trajectory, and at some time it goes back to the original position. Okay. Well, I will show some small movie. Okay. Starting from this, particles spreads in the box. Okay. At the time 100, we reverse the momentum vector. Then it backtraces its trajectory. And finally, it goes back to the original position. Okay. This is a very simple example of classical mechanics. Now, we consider partitioned cellular automata for studying such problem. Here we use triangular PCAs, partitioned cellular automata, and square PCAs. TPCA space are like this. Each cell has 3 parts, and depending on the neighboring 3 parts, each cell changes its states. Likewise, square partitioned cellular automaton is like this. In this case, depending on 4 neighboring parts, the next state of the cell changes. Okay, therefore very simple. And elementary ones are the simplest subclass of these PCAs. A PCA is called elementary if it is rotation symmetric and each part has of a cell has 2 states, only 2 states. Therefore, a local function of an ETPCA elementary triangular partitioned cellular automaton and the elementary square partitioned cellular automaton is thus described by only 4 or 6 local transition rules. For example, these 4 local transition rules describe a specific ETPCA. Likewise, these 6 local transition rules defines a local function of an elementary square partitioned cellular automaton. Therefore, both models are very simple. Global functions of these PCAs are defined usually, as usual. Applying a local function small f to all the cells, a global function large F is induced. For example, if a triangular partitioned cellular automaton has these 4 local transition rules, then by applying these rules to this configuration, it evolves like this. Okay. Definition of reversible one is like this. A PCA is called reversible if large F global function is injected. And it is very convenient to use such partitioned cellular automaton because the following proposition holds. In a PCA, its global function is injective if and only if local function is injective. Therefore, if there is no pair of local transition rules having the same right-hand size, then it is reversible. For example, this local function, look at this local function. Then there is no pair of distinct two rules that have the same right-hand size. Therefore, this local function is reversible cellular automatons one. Okay. In the case of ETPCA, elementary triangular partitioned cellular automaton, we can choose these right-hand side. Okay. For example, if one particle comes here, then next state, possible next states are these 8, like this. Okay. Therefore, there are 256 kinds of ETPCA in total. For example, ETPCA 0347 is like this. By reading the right-hand side pattern as a 3-bit binary number, we can give a ID number 0347. Okay. Similarly, elementary square partitioned cellular automaton is described by 6 digits of 6-digit hexadecimal number. For example, 01CAEF. Anyway, there are about 65,000 kinds of ESPCA in total. But reversible ones are relatively few. For example, in the case of ETPCA, there are 256 ETPCAs, but only 36 are reversible ones. Now, in the following, we investigate how inverse function of inverse global function is expressed in terms of the global function f based on their T-symmetry. Okay? This is a main topic of today's talk. Okay? How inverse global function is expressed. Okay? Now, let conf k is the set of all configurations of ETPCA in the case of k is equal to 3, or ESPCA in the case of k is equal to 4. A function h that is from configuration to configuration is called an involution if h is an identity function. If we apply h twice, then it becomes identical. Such a function is called involution. Okay? Now we define T-symmetry on reversible cellular automata. Let P be a reversible ETPCA or ESPCA whose global function is large F. If there is an involution H that satisfies F inverse is equal to HFH, then P is called T-symmetric under H. Okay. Note that if F inverse is HFH, then F minus T, F to the minus T is equal to HF to the Tth H for any T. It is proved by a simple mathematical induction. Well, I will show again classical mechanics. At first, particles are lower left corner, and evolve it some time steps. Then particles spread in this box. At this point, we assumed that all the momentum of these particles are reversed. This reversing operation is a kind of involution, okay? Involution H. Because if taking this involution twice, then of course goes back to the original one. Therefore, reversing momentum vector is a kind of involution. Okay? And if we assume such involution is applied to this state configuration, okay, then evolve the same time steps as before. Then it goes back to the original position. Okay? But momentum vector are different from the original. But anyway, once again, we apply the reversing operation of momentum vector. Then we goes back exactly the same configuration. Okay. In classical mechanics, involution H corresponds to reversing operation of momentum vectors. Okay. A similar situation occurs in elementary triangular partitioned cellular automaton. Of course, this is a reversible one. For example, if we start from this configuration consisting of only one particle, and we assume it evolves for several steps, and then we apply an involution H that corresponds to reversing moving direction of particles. Then it becomes such configuration. Then evolve by same steps as before. Then it goes back to the one particle configuration. And further, apply this involution H, then it becomes exactly the same configuration of this one. Okay. Well, sorry. Here we also introduce other involutions besides H reverse. Okay? This involution H is a reversing moving directions operations. Okay. Besides H rev, we prepare H reflection and H complementation in ETPCA. H rev is reversing moving directions of particles. For example, look at this particle. Okay, this particle is moving towards downward direction. Okay, this one, this pink one. Then by H rev, this particle goes back to the upward direction. Okay? Other particles are also like this. H rev is reversing the moving direction of particles. Okay? This operation is defined by F0257, ETPCA 0257. Okay, because this local transition function makes this particle's direction backward, okay? And other rules are also so. Therefore, by applying the global function F0257 of ETPCA 0257, we can realize H rev. The next one, H reflection, is an operation of taking a mirror image by taking, consider, for example, this configuration. And then by taking H reflection, we have this one. Okay. The third involution, H complementation, is an operation taking 0,1 complementation. Okay, like this. And by combining these three kinds of operations, involution operations, we can make many ETPCAs time symmetric. Okay? Likewise, for elementary square partitioned cellular automata, involutions H rev, H reflection, and H complementation are defined similarly. Note that in elementary square partitioned cellular automaton, H rev is defined by the ESPCA 08 CADF. Okay. H reflection and H complementation are similar to the previous one. And we have the following T-symmetry results, but this page is slightly complicated. Therefore, I use this one. In ETPCAs, elementary triangular partitioned cellular automata, there are 36 reversible ones in total. Among them, 8 are T-symmetric under H rev reversal. 24 are T-symmetric under H rev H reflection, such a composite involution. Under this composite involution, 24 are T-symmetric. Likewise, 8 are T-symmetric under H reversal, H complement. Okay. And 24 are T-symmetric under H rev, H reflection, H complementation. And remarkably, there is no non-T-symmetric under the above involution. Therefore, all 36 ETPCAs are T-symmetric in either of these 4 involutions. In the case of ESPCAs, elementary square partitioned cellular automata, about 58% of the 1,500 and so on reversible ESPCAs are T-symmetric. However, it is not known, it is an open problem, whether the remaining 42% are T-symmetric under some other involutions. This is an open problem. But anyway, many, about 58% of these reversible ESPCAs are T-symmetric under these 4 involutions. Such a property is somewhat resembles in CPT symmetry in physics, charge parity and time reversal symmetry. They very roughly corresponds to H comp, H reflection, and H reversal. But of course, I do not today. I do not go further on this problem. Okay. Now I will show 4 examples of T-symmetric ETPCAs or ESPCAs. And we argue how T-symmetries are used to analyze or design inverse processes. The 4 examples are as follows. First one is ETPCA 0527. It has the following local function, local transition function. If we start from one particular pattern, like this, it generates hexagons. Okay? and also it generates one particle, okay, like this. Therefore, many hexagons are generated from one particle, okay? If we denote this configuration alpha 0, then at time 18, there are 3 hexagons. ETPCA 0527 is T-symmetric under H-rev reversal. Therefore, only by reversing the direction, moving direction of each particle, we can obtain backward evolution process like this. Therefore, if we want to go to backward from alpha 18 to alpha 1, 0, going to this blue arrow, it is also this backward evolution is performed by H-rev F18th and H-rev. Okay? This path is commute by this path. Okay? Namely, F to the minus 18th is H-rev F18th H-rev. Okay? Such a commutative law holds. Reversing the moving directions of particles, hexagons converge to a single particle. Okay? Well, I will show using the Gori simulator. Okay? This is the space of ETPCA 0527. From one particle, it generates many hexagons, okay, like this. Okay, we copy. We copy this pattern. Okay, and then add another layer and prepare. Sorry. This is a cellular space of ETPCA 0257. It performs H-rev. We paste the previous configuration in this cellular space. Okay. Then in this cellular space is not interesting because each particle goes back and forth reciprocally. Therefore, not interesting. But it performs H-rev. Therefore, we apply this global function only once. Okay. Then again, copy this configuration and go back to the original ETPCA 0527 space, okay, and paste it, okay. Then original pattern still expanding, but the lower pattern goes back to the evolving process, and finally goes back to only one particle. Okay. Anyway, in this way, sorry. Sorry, some by using the simulator, we saw that going back to the original pattern at time t is equal to 0. First, we apply href and apply the same forward global function to this pattern. And then finally, href is applied, original pattern at time 0 is obtained. Okay. Next example is on elementary square partitioned automaton 09457F. This is also T-symmetric under href. Starting from a 3-particle pattern, it generates a random-like pattern with many gliders. Okay. Likewise, as before, if we go back to this configuration, to the original one, we first apply href and then forward global function 100 times. And then finally href, then we have the original one. Okay. I also show this one. From the 3-particle pattern, it generates chaotic pattern and with many gliders. Okay. Again, copy this one. Okay. And prepare another layer. 08CADF that performs href. By using this cellular automaton, we can apply href by applying only once. Okay. And copy this configuration and go back to the original one. Okay. The paste this. Okay. Then, of course, original configuration expands, still expands, but the obtained one goes back to the 3-particle pattern. Okay. The next example 3 is ETPCA 0347. This is T-symmetric under href reflection. Okay. Therefore, we also apply H reflection in addition to H reverse. Okay. In this cellular space, there is a glider, a space-moving pattern in it. And it is known that ETPCA 0347 is computationally universal. In this cellular space, by colliding two gliders, making a head-on collision like this, then we can see three gliders are generated. From this configuration, gamma 30, if we apply H-rev, H reflection, then we have such configurations. And applying F0347 30 times, then we have two gliders. Namely, from two gliders, three gliders are generated. But by the nature of T-symmetry, we can also have a process from three gliders to two gliders. Okay. Here are two gliders, here and here. Okay. By colliding it, three gliders are generated. Okay. Symmetrically, there are three gliders, here, here, and here. Okay. By colliding three gliders like this, we have two gliders. Okay. These two processes are symmetrically obtained because of T-symmetry of this cellular space. By using such property, we can obtain a glider gun. Okay. By too fast. Anyway, by colliding two gliders like this, three gliders are generated. And one glider is emitted outside. And the remaining two gliders are used to generate three gliders, okay, like this. And symmetrically, we can obtain glider absorber. Absorber is a backward process of glider gun, okay? By colliding three gliders in this way, one of three is erased reversibly. Okay? Okay. In this way, glider gun and glider absorbers are obtained. Therefore, of course, this two process from two gliders, three gliders are obtained, and from three gliders to two gliders are obtained. These two processes are symmetric, and likewise, glider gun and glider absorber is also symmetric by applying HREF reflection from glider gun glider absorber is obtained, and vice versa. In a similar way, switch gate is realizable in ETPCA 0347. Switch gate is proposed by Fredkin and Toffoli. From switch gate module, switch gate inverse switch gate module is automatically obtained by applying href okay? Using two switch gates and two inverse switch gates, so-called Fredkin gate is obtained in this way, okay? A final example is on ESPCA 02C5BF. This is also T-symmetric under H reflection, okay? In this cellular space, colliding a signal with a block is this one, okay? A signal consists of two particles, and the block consists of 8 particles. The colliding this signal to a block, it makes a left turn like this. It is known that ESPCA 02C5BF is also computationally universal. By colliding two signals like this, we can obtain a kind of logic gate, so-called interaction gate. Okay. It mimics this billiard ball model. If only one ball comes from, for example, x1, then it goes straight ahead. But two balls come, then its trajectory shifted slightly. Such a process is simulated by colliding two signals in this cellular space. Also, similar to the switch gate and inverse switch gate, we can compose inverse interaction gate from interaction gate by applying href. Okay. Okay. I will show again. Left-hand side, there is a interaction gate. Okay. If two signals come, then also two signals goes out from this and this port. Only one signal comes from this, then it goes from this output port, like this. And inverse I gate is obtained by applying hreflection to this I gate. Okay, this is almost symmetric. Okay. And using these two gates, rotary element is composed. A rotary element is a very simple logic element with 2 states, 1-bit memory. 2 states are distinguished by the direction of this rotatable bar inside. Okay, vertical state and horizontal state. Okay, and if a particle input signal comes from the direction parallel to the rotatable bar, then it goes straight ahead and state does not change. But if a signal comes from the direction orthogonal to the bar, then the signal turns right and the bar direction of the bar changes. Okay, such a very simple operation. Okay, and rotary element is useful for making reversible Turing machines. And we can see in the following slide, RE can be composed of interaction gates and inverse interaction gates, like this. Today, I do not explain the details of this operation, but anyway, there are 4 interaction gates here, 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 and here. And the inverse interaction gate are here, 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 and here. Okay, by using 8 gates in total, we can compose a rotary element. Okay, this is a rotary element. And by using rotary element in this way, we can compose any reversible Turing machine in this way. This is, of course, very simple example. T parity. It checks if the input unary number is even or odd. But any reversible Turing machine can be composed in this way. I also show this. At first, I show rotary element is composed of this is a interaction gate and inverse interaction gate. Okay, and the input signal is coming from here, west input. And to remember the memorize the state of this rotary element, this signal is used. Okay, and in order to indicate the state, additional states is used. Now this element is in the vertical state, and signal is coming here, and the interaction gates it interacts, okay, and changes its state from V to H. Okay, speed up a little bit hard to see, but anyway, signal goes back and forth, and rotary element is simulated correctly. Yes. Okay. By using such a rotary element in this way, we can compose any reversible Turing machine. Okay. it takes very much time. Therefore, I speed up. It takes about 1 million steps. Therefore, I accelerate. Finally, the input is accepted. Okay. By using T-symmetry of this cellular space, we can also obtain an inverse reversible Turing machine. Okay, by applying H reflection to this configuration, this is a forward Turing machine. To the forward Turing machine, if we apply this involution, then we can obtain a backward reversible Turing machine like this. This Turing machine undoes or uncomputes the original Turing machine from accepting state to the start state, start configuration. Okay. This one. The upper Turing machine is a forward Turing machine, but it is in an accepting state, accepting configuration. And by mechanically applying H reflection, we have an inverse Turing machine. From accepting configuration, it uncomputes, undoes the computing process backward, and therefore it finally goes to the start state. Okay? Of course, it is a bit very hard to recognize, but anyway. From accepting state, it undoes computing process. Signal is flying here, okay, like this, okay. Anyway, it will take more than 1 million steps. I accelerate. It's already start state once again. The lower Turing machine is now uncomputing, and finally it becomes start state. Okay, it will soon become now it becomes the start state, and the uncomputing is done in this way. Okay. Now, the framework of PCAs is very useful for investigating T-symmetry in reversible CAs. It is because reversal operation of each particle is very simply done in partitioned cellular automata. Okay. And we saw all reversible ETPCAs, and about 58% of reversible ESPCAs are T-symmetric under several simple involutions. Several means H-rev, H-reflection, and the H-complementation, and their compositions. Okay. However, 42% of reversible ESPCAs T-symmetric or not is unknown. It is an open problem. But anyway, obtained results are used, very useful for analyzing inverse processes and designing inverse functional modules in these reversible PCAs. These are the references. Okay, thank you for your attention. That's all of my talk.
Thank you so much, Professor Kenichi Morita. That was a very nice talk. And now we want the audiences to ask some questions. If you have any question.
One question.
Yeah.
Sir, Morita, sir. Thank you very much. Session is very awesome.
You're welcome.
Okay, well, basic question, sir. So
Yeah.
actually, what is happening that reverse cellular automata is decreasing the image, decreasing the pattern, right?
Decrease.
Exactly at which step it is happening? Any mathematical justification is there? Decreasing is happening,
yeah,
no?
decreasing. In the case of decreasing, sorry. Again, I use I will use again. Okay.
It is
degree when it is decreasing, then
decreasing. At which step it will start? Any mathematical
no
justification?
yeah, if it decreases, it must then increase. For example, I will show another.
It is false.
No, ever decreasing is
Slide
no,
number.
sorry. I will show this one. For example, decreasing, but finally it must increase because of T-symmetry or reversibility. It cannot decrease forever. If some configuration size decreases, then at some time it turns to.
Any mathematical justification is there? Decrease.
Pardon me, I cannot hear your voice well.
The decrease first initially image is increasing, right?
Yes.
Then after that it will decrease.
At some time it must increase.
At which step it is happening? Any mathematical justification is there? At which step it is happening?
Sorry, I cannot hear your voice well.
Okay, sir.
Okay, I can try. Sir, what he is asking is, you are saying that it is going on increasing, decreasing, and then increasing. So he's asking that at which step it will stop decreasing and again start.
Yes. Any mathematical
calculate it. Can you calculate it?
Of course, it depends on the local function or global function of the cellular automaton. But it can be proved that if some configuration size is decreasing, it must increase at some time. Okay. When it increase is depends on its local or global function. Is it can be your question's answer? No?
Sir, maybe if your local and global ruler is fixed, then in that case, can you calculate that when this phenomena will happen, if it is a reversible C?
Yeah, yes. But generally, behavior of cellular automaton is very complex. Therefore, exact time is very hard to calculate. But upper bound can be calculated very easily because number of configurations whose size is limited is of course finite. Therefore, such a number time is limited by such a number. But exact at what when is very difficult to calculate without simulating the process. Okay? But anyway, upper bound can be easily calculated.
Okay, sir. Thank you. Thank you.
Sumita madam probably has some questions. So, ma'am, please go ahead. Sumita Basu madam probably she has raised hand.
Mhm.
She might have some question. And can you hear me? Okay. If not, is there any other question from other audiences?
Ma'am, I want to say one thing.
Mhm.
Actually, you, Kamalika and her team is making India strong in cellular automata research domain. Thanks to Kamalika, ma'am. Really, you are putting 100% effort, your team. Really, thank you very much.
Thank you so much. Sir, Professor Morita, actually, I
Yeah.
have two questions. One
Okay.
is, what are some emerging areas of the research that combine the study of time reversal symmetries with other type of symmetries or computational models? Some other emerging areas that I want to know that can combine the study of time reversal symmetries with the other type of symmetries or computational models.
Other types of computational model other than cellular automaton, no?
Yes. Like
Yeah.
we can combine the time reversal symmetries with some computational models, say cellular automata. So, is there any some other emerging areas that can combine these two?
Yeah. Any computational model, reversible computational model, have some kind of time symmetry. Yeah, for example, switch gate. For example, switch gate has its counterpart inverse switch gate. and these inverse pair is very important to design a larger functional module. And also, I am now studying reversible logical element with 1-bit memory, and its time reversal properties. Therefore, in any case, any reversible computing system has some kind of time symmetry property. But still, we need still further investigation on that. Okay. Up to now, I am studying time symmetry in cellular automaton. But such a study can be extended to any reversible systems, I think.
Okay, thank you, sir.
Excuse,
We have one.
I
Yes,
yes. Am I
yes.
audible now?
Yes, yes,
Yeah.
You are audible.
Well, I have one question or suggestion. What do we say that, like in one-dimensional, say, in the case of reversible cases, sir, we have that it is the global function. Right? The global function is it's like it forms a cycle. It comes back. Is the same thing happening over here also? I think so that there will be a such reversible function. We can find the global transition function will be a reversible one, and which I mean a cyclic function.
Not always cyclic function.
Am I clear? Is that computable? That's what I. Can we search for such cyclic functions, which are that will also this can be done for in the one-dimensional case.
Yeah. In fact, one-dimensional case, and of course, infinite. If we consider infinite array of cellular automaton, then some configurations are cyclic, but many configurations are cyclic. Many configurations are. Therefore, in such a property, from such a property, we can prove even in one-dimensional case, a reversible cellular automaton is computationally universal.
Yes, that is possible. So, is that method, can it be used here also? That's my question.
What?
I mean, that method of finding cyclic, I mean, a cyclic global transition function. Is it possible to find such global transition functions here also? Cyclic global transition functions.
Cyclic, of course, very special reversible cellular automaton has cyclic function. All configurations have cyclic function, but in generally, reversible some configurations have cyclic, but others are acyclic. Because of acyclicity, universal computing ability can be obtained. Okay, if all configurations are cyclic, then it is in general
I
non-universal.
mean, the global transitions are cyclic
Glo
functions. If the global transitions are cyclic functions. That is a very restricted condition, I suppose.
Yes, very restricted conditions. Under such conditions, maybe all the configurations are cyclic.
So should we conclude that even if there are acyclic such global transition functions, there may be acyclic global transition functions which are also reversible. Can we conclude that? I mean, are there acyclic global transition functions which are also reversible?
Yeah, of course, very restricted ones have, sorry, I will show you this one, not this one. This is a very trivial example, but this cellular automaton is performs H level. Therefore, it has only every configuration has cycle 2, and there is no acyclic configuration. Therefore, very limited ones are all the configurations are cyclic. But these cellular automaton is not interesting in my point of view. Acyclic
ones are of your interest. You are interested in acyclic ones.
Yeah, acyclic ones are of interest in my point of view.
Okay. Thank you. Thank you very much.
You are welcome.
Okay, Sir has some question.
Yeah, I have some comments question. Kenichi, this Sukanto. So, as usual, I am mesmerized by your talk. It is excellent. I have a few questions. While you are discussing about T-symmetric ETPCA, in one case, you have said that ETPCA, it can show chaotic behavior. ETPCA can show chaotic behavior. So, my question is that T-symmetric ETPCA, which are reversible, can they be chaotic also?
Yeah, chaosity is also an interesting problem, I think. There are, for example, computationally universal reversible PCAs that have no chaotic pattern, that produce no chaotic pattern. But on the other hand, there are also computationally universal reversible cellular automaton that have chaotic, that can produce chaotic pattern. Therefore, in my studies so far done, producing chaotic pattern or not is not related to computational universality. Can it be the answer for your question?
But it's all right. But can it be reversible?
Yes, of course. Reverse. In the case of reversible, there are chaotic one, but and non-chaotic one. In both cases, we found computational universal reversible cellular automata.
Okay. So therefore, ETPCA, they can be chaotic as well as reversible, but not universally computable.
Yeah.
In this
Yeah.
in this context, actually, I have one question that can this type of irreversible CA exhibit chaotic behavior?
Yeah. There are, of course, many irreversible ones, and I have not so far studied exhaustively, but there are many irreversible ones that shows chaotic properties also, of course.
So reversible and irreversible, both type of CAs can actually show this chaotic behavior.
Yeah, in both cases, chaotic behavior appears. Okay.
Okay. And one last question we can take. We have one question in the chat box. What are the application of T-symmetry, ETPCA, and ESPC?
Application?
Yes.
Of course, I have shown a few applications in my talk, but in any way, we can use T-symmetry to construct, design inverse functional module. Therefore, I think there are many applications for that purpose. Okay. But of course, I have not studied, fully studied their applications. Only so far, 10 or such, I have 10 or such kinds of applications. But anyway, I think there may be many applications. Okay.
Okay. Kamalika Di has raised hand. Kamalika Di probably has a question.
Yeah, you say there are time is actually over, so it's just a question to actually both the speakers. I'm listening to both the talks, and Professor Shulkole was talking about reversible computation, where there should not be any cost of computing as such. So kind of the computation, the power dissipation, that should be actually zero. And now Morita is talking about the universal computation, where he is indicating that actually the reversible systems, the cycles, those are actually not of much concern to us. Rather, the acyclic behavior in those kind of CAs are of interest to us. But if this acyclic behavior is there, then obviously it will not come back to the initial state. So can I combine these two notions together somehow? Like we are interested in reversible computation, which can also perform universal computation in some sense. But in the case of reversible CA, actually the CAs that you have shown us, that where in that case, some parts of the cycles are reversible, but those are very trivial. Rather, the acyclic parts are more interesting to compute universal computation rather.
Yeah.
So what are the overall implications it can bring out? This is my
Mhm.
question to both of you.
Mhm.
So can reversible CA play a role rather in reversible computing, or it will be a kind of, it is a hypothetical situation? Because these two notions seem to a little bit contradictory to me.
Mhm.
What
Yeah.
I feel is,
Mhm.
okay, Professor, well, Professor Morita, please go
Mhm.
ahead. Then I'll voice my
Yeah.
thoughts.
For example, to construct a reversible Turing machine like this, we should use acyclic, not a cyclic property, because any universal computing system has undecidable property, that is, when it holds is undecidable. Therefore, we have to prepare a very long computing process. Therefore, for example, to start this computer, we should activate this computer by a signal. For example, this is a signal. Okay, by this signal, this computation is initiated. But go back to the past. This signal comes from the very far away, infinitely leftward. This signal must come. Okay, and by this signal, computing start. And when it accepts, then accept signal goes out from this output port. And if nothing is put here, this output signal goes, in this case, leftward infinitely. Therefore, this whole configuration is acyclic. Okay. Therefore, when we want to construct a universal computing system, such acyclic property is necessary. Okay. If only limited lengths of cycles are available, then universal computing is not possible. Therefore, such acyclicity of system, reversible system, is a very important property for composing universal system.
If
This
I
is other.
Yeah, if I understand correctly,
Mhm.
reversibility, to answer the question, reversibility and acyclicity are not contradictory, because reversibility means that the transition function is such that you can reverse it. Even if it is acyclic, you can come back. So the information lossless part remains, even if it is acyclic, as long as it is reversible. So I think that will clarify what your confusion is. Acyclicity is needed for universality to cover the entire function state space. But if each step
is the transition is reversible. At each step, wherever you reach, you can reverse that. So I don't think they are contradictory.
Okay, thank you. Thank you, sir.
Thank you very much for organizing this and inviting me.
Thank you, ma'am. Thank you so much. We could not take much of your questions because time was running out. So I'm sorry for that.
No, that's okay. Professor Morita, I learned a lot from your talk. I have very little, what should I say, interaction with cellular automata. Once for one of my projects, which was on fault simulation for asynchronous sequential circuits, I had used cellular automata, and in some sense the universality comes into picture where we can generate very good quality pseudo-random test vectors. But at that point of time, this was many years ago, at that point of time, we did not study the quality. Now with the quantum computing, you have true random number generators and quality of pseudo-randomness. There is a lot of scope for studying that as well, because pseudo-random numbers or random numbers are very, very useful. In terms of universality and reversibility, may I ask what are your thoughts on random number generation by these sort of automata?
Yeah, of course, pseudo random number can be generated, but I have not yet tested their quality. But anyway, in many reversible cell automata, chaotic pattern often appears. In the chaotic pattern, there are many random part. Therefore, pseudo random number can be, of course, easily generated by
yes, we got
easy.
We got fairly good results, but there were some holes, some places where we could not reach. The reachability problem was also related to that. Anyway, I think we are running out of time, but this is a very rich area, and it's a good thing that this is being promoted by this sort of webinar series. Okay, we will get in touch with Kamalika.
Yeah, thank you, ma'am.